Hello students, I want to talk a little bit about exponential functions and logarithms. Make that a Roman numeral number 1 in case this goes on a couple pages. So the thing about these things is, exponential growth, exponential decay. And you can think of these things as being like an amount of something occurring in time on the independent, what we usually call the x-axis. Right? Here you got an amount of something growing in time, and it's growing exponentially. Here you got an amount of something decaying in time. It's decaying exponentially. The thing is for exponential growth, these guys are all going to have a set doubling time. So look, see at time 0, I started with this much. Well, at some point, in time, I'm going to have twice that much, right here. This is the doubling time, and all exponential growth has this notion of a doubling time. So when I go that much time again, like this far, then it should double again. And when I go that far again, it should double again, etc. Right? That's the doubling time, and it's a set doubling time. So that's why every exponential function can be written like y equals c times 2 to the t over d, where d is the doubling time. Every exponential function can be written in terms of its doubling time like this. C is the initial amount. It's the amount at time 0. That's a C times 2 to the t over d. Look, suppose the doubling time were 10 years. Then look, when the time is 10, 10 over 10 is 1, and 2 to the 1 is 2. That's exactly when you take the initial amount and multiply it by 2 is at t equals 10 years. So another thing about these things is, I'll just go through the exponential growth thing, and then we'll find that the exponential decay thing works very similarly. Maybe since it's all up here at the top of the page, maybe we'll just say this right now. With exponential decay, these things are going to have a half-life. So, here at time 0, I started with this amount. Well, at some point, I'm going to have half that much in this amount of time, right? This is my half-life now. And every time I go that period of time, like when I go that period of time again, I should be half again. And that period of time again, and I should be half of that. And it's half, half, half. So these guys have a set half-life. And for that reason, they can all be written, if you know the half-life, then they can all be written as c times 1/2 to the t over h, where h is the half-life. And of course, c is the initial amount again. The amount at time t equals 0. So for instance, say the half-life were 10 years. Then look, when t is 10, 10 over 10 is, just use a different number. Suppose the half-life were 5 years. When t is 5, 5 over 5 is 1. 1/2 to the 1 is a half. That's exactly when you're taking the initial amount and multiplying it by half. Is at 5 years, exactly the half-life. And it's going to keep on getting multiplied in half every 5 years. So that's why every exponential decay function can be written in terms of its half-life. But of course, you have to know the half-life, h, to write it like this. So then you got to realize that these things, let's go back to exponential growth now, they grow at a constant percent, like 5% a year or 7% every 6 months or these kind of things, right? They grow at a constant percent. And so for that reason, they can all be written also, right? I mean, the same function that can be written as doubling time in this manner, the same function could be written in this other manner in base E, where K is called the relative growth rate, and it's basically just a proportion. You know, it's like the percent written as a proportion. You know, like K equals, 0.06 or something like this, right? It's the relative growth rate, and, if this is just a T here, then that would be 6% per year, because every time T is, for instance, when T is 1, this is e to the 0.06, which turns out to be, approximately 1.06. And so, this thing is growing by 6% per year. But the thing is, like for instance, in half a year, it's grown half of 6%. And these kind of, right? So, I mean, this is going to be true in any proportion of a year, just like this is true in any proportion of a year. So, for instance, up here where I was going to have a function with a doubling time of 10 years. Let's go back up there for a minute. Let me see now. We're 7 minutes into this. Let's actually come up with a doubling time of, 7 years, just to keep the arithmetic more interesting. And so, the function will look like y equals c to the t over 7. Well, think about how you would find the half-life right here. Well, excuse me, you already have the half-life of 7. See how you would find the relative growth rate. You would literally take this guy and say, well, look, I know that e to the ln of 2 is 2. So here's my 2 to the t over 7. In other words, I'm going to transform this thing into an exponential form base e. Now see this is like an ln of, this is like, something's not working with this pen, c e to the ln of 2 over 7 t. So when I take that ln of 2 over 7, see how this is now y equals c e to the kt? So that's my k down here, is this ln of 2 over 7. And this is point, and I'll go out like to 6 decimal places, 0.099021. And even further, like I've meant, t. So, like I've said in class, this is called a relative growth rate. And so its annual growth rate is 0.099, but it's actually growing at better than 0.099 because, the population is growing relative to the size, and the size is growing constantly in time. So anyways, we see how to take something that's, if we know the doubling time, we can write it as a doubling time exponential function. And then it's very easy just to translate it into base E. And then once you're in base E, you can see that the relative growth rate is, 9.9% roughly. That's how much it's growing every year. But it's actually going to grow it, a little bit better than 9.9%. Because like I was saying, every 3 months the population has grown. So it's 9.9% of a population that's already gotten bigger before the first year is even up. So that's why it actually is growing at e to the 0.099, that number minus 1. So when I take second e to the 0.099, that's like 1.1040. And when I subtract 1 now, so this is, 1.1041 like this, minus 1. That's giving me the 0.1041. This is the actual annual growth rate. Because its relative growth rate is 9.9%, but because, like I keep saying, the population is growing, before t is even 1, the population is already grown, so it's gaining 9.9% of an already larger population, which makes, the annual growth rate more than 9.9%. It's actually 10.41%. Sorry, that's off the screen there. Let me get that on there for a second before I go over the other side. Now, I think since this video is getting awful long, I don't know that I'm going to go through and talk about everything over here because it's all the same game except it's 1/2 to the t over h. The only thing you really got to remember over here is, this 1/2 is like 2 to the negative 1. See that 2 to the negative 1? That is a half. So here's my half to the t over h. In other words, this is 2 to the negative t over h. That's another way to write that. But, since this video is going to be getting pretty lengthy already because I saw some other stuff I want to do with, the growth here. So all we've seen is if you have the doubling time, you can write it in base e. And then once it's in base e, you can see the relative growth rate. And then you realize it's actually growing more than that annually. And so you can get some information out of there. Now, like just going along with this again, for instance, how long until the original amount has decayed to 85% of its original amount? How long until, or excuse me, this one's not decaying, this one's growing. So how long until it's grown by 85%? So now then, my initial amount C has grown by 85%, so that's 1.85C. So I would say 1.85C equals CE to the, all that stuff. It's actually easier just to do it in base 2 because that way you don't have those big long decimals chasing through the whole problem with you. But this is 1.85CE to the 0.099021. T. This is 0.099021T. So the C's cancel out, and now you got to know about logarithms. The only way to write this exponent, 0.099021T, is as a logarithm. The base on that logarithm is e, and that's what a logarithm is. It's an expression for an exponent. So this is, the log base e means the ln, of course. And now I'm dividing by the 0.099, right? So again now, if I didn't keep this number with all like 10 decimal places of accuracy, which I actually didn't, then you're going to pick up some slight little rounding error. I'm going to just turn off the video for a second and recompute this number with all its 10 decimal places. Yeah, it's the ln of 2 over 7, right? From up here, the ln of 2 over 7, that was that 0.099 number. So what I'm going to do this time is, oh crap, the ln of 2 over 7. This time I'm going to store this into my calculator. So I've got it there to use. So now when I'm down here, I'm going to do the ln of 1.85. And when I divide by 0.099, I'm recalling out of my calculator all those decimal places of accuracy. And we get 6.21. Here, let's go a few more decimal places because I want to do this in a different way in a moment. 6.21, 212,677. 212,677 to 6 decimal places. Because I want you to realize that you could have done this with this one up here with the base 2. And it would have actually been easier. How long till it grows by 85%? Well, again, y is still 1.85c equals c, but now we're using this one, which is 2 to the t over 7. Right? If you remember, it's the same exponential function. It's the same, so we better get the same number. So now then, when we divide both sides by c, again, the only way to write the exponent is as a logarithm, but this time it's log base 2 of 1.85. Now you won't be able to do this with your calculator without the change of base formula. It says it's the log of 1.85 over the log of 2. And that's t over 7, the exponent. The exponent has to be written as a logarithm. Now multiply both sides by 7. T is the log of 1.85 over the log of 2 times 7, right? You watch, it's going to be the same number. So we get the log of 1.85 divided by the log of 2 and multiply by 7, and it's 6.212677, right? It's the same. Of course, it better be, otherwise something's wrong. So hopefully this is a nice little introduction. It's a long one, 17 minutes in here. But you want to realize all exponential growth has doubling time. You can write it in base 2. It's also, got this growing at a constant percent, so you can, get at that constant percent growth with these exponential base e functions. The k is the part that's telling you the relative growth rate. And so what I did is I took this thing that was in base 2 and translated it into base e. And after we do that, we can read the relative growth rate right out of there, as well as, with a little arithmetic, figure out what the actual annual growth rate is. So that's all good stuff to know. Then you got, questions like this: how long until it's grown by? And this all could have been done with the decay function. How long until it's reduced to 85%? It's just the same thing, but you're using this one. This one can easily be written in base e, just like I did this over here, and you should do it. Practice it. See, look, it's written in base 2. Everything's the same except the exponent is negative t over h instead of, it'll literally be the exact same if you really work one out on your own. Anyways, how long until it's grown by 85%? Well, the initial amount is grown by 1.85. The initial amounts just cancel out. It turns out it doesn't matter how much you started with, the time's going to be the same. So we did this, we used the base e one to figure out, and then we said, oh look, it would have been easier just to use the equivalent exponential function in base 2. But then you needed the change of base formula. And of course you get the same number. So you should be able to do that. That's really not that big a deal, I have to tell you. There's not even any calculus there. It's precalculus. I think I'm probably going to have a second video when I think of some couple other things I have to say here.